Algebra 2. This is 10.2.2, which is the properties of logarithms. So in this section, we'll be using the properties of logarithms to simplify and evaluate these functions. And the thing about logarithms, their properties are very similar to the properties of exponents, and that makes sense because logarithms and exponents are the inverses of each other. They're very closely related, so in some ways they work the same way. So with each property, we'll try to go through some examples to show you how they work and how you can use them. So the first one is the product property, and what this says is that if x, y, and b are all positive, and so x, y, and b, well, b is going to be the base on our log, and then x and y will be parts of the argument of our log. So if all the numbers involved in this logarithm are positive and b is not equal to 1, then if x and y are multiplied by each other and b is the base, and so you have something that looks like this. If you have log base b of xy multiplied by each other, what you can do is you can split that up into two separate logs, one and both of them having a base of b, right? So both of these have a base of b, and then separating the different pieces of your argument, right? So we would have log base b of x plus log base b of y. So this multiplication between the two pieces of our argument, the x and the y, the multiplication between the x and y, that'll turn into addition between two separate logarithms, okay? So this only works when you have two things being multiplied by each other like that. And it also works for natural logs. So in this first example, our directions are to write the logarithm in expanded form, right? And so this might be the kind of a problem that you would see on your homework. And so we have log base 3 of 2x. And so what we have right here is 2 and x are being multiplied by each other. So we can rewrite this using this product property that we just talked about. And we can say this is the same thing as log base 3 of 2 plus log base 3 of x. And so that's all we had to do, and that's our answer, and we're all done. So some things that I want to draw your attention to, notice how they both have a base of 3, right? And you have a base of 3 to start the problem with, and then you have addition between the two. So that's key, and then one of them has a 2 and the other one has an x, and you're all done. So something that's related to that is the quotient property of logarithms. And so what this says, given all the same conditions, if you divide x and y, then you can separate them into two separate logs, and you can use subtraction. So here, notice our bases are b the whole way through, right? Everything has a base of b, and then it's log base b of x minus log base b of y. And so what's on top of your fraction, or what's your numerator, goes with the first log right here, and then what's on the bottom of your fraction, or what's in your denominator, goes with the second log after the subtraction sign, okay? And so that's one way that you can separate those. So typically whatever's positive, you can associate with beginning the subtraction, and then whatever's negative or whatever's on the denominator of your fraction ends up being negative when you change it to subtraction. And then we have the power property of logarithms. And so what this says is that if you have any real number r, and that r is an exponent on your argument, right here we have log base b of xr, you can take that r and you can throw it in front of your log, right? So we took this r, and let's see, do this in a different color. It's kind of like you take this r and you throw it to the front, right? And so that then you get r log base b of x. So whatever number you had as your exponent goes in front of your log, and then the argument at the end no longer has an exponent. Okay, so we have these examples here, and we can run through them with the first three properties that we just talked about. So for the directions for these is we want to express these as a single logarithm with a coefficient of 1. So for example 2, the first one, everything has a base of 2. So log base 2 of x squared plus log base 2 of y. And then we've got this addition in between. So if it's addition, well, then that means multiplication. So then how I could rewrite this is log base 2 x squared y. And that's one logarithm, or that's one argument right here. X squared and y are connected. And that's my answer, and I'm all done. So this next one, log base 5 x cubed minus log base 5 y to the 4th. Well, both of those are log base 5, right? So my answer is going to be log base 5. And then I have subtraction between the two, so that's going to mean division. So it's going to turn into x cubed over y to the 4th. And that's it, and we're all done with that one. Now, this next one, 4 log base 5 to the x. So if you remember, our directions were, at the very beginning, if I scroll just back up quickly to the beginning, is that we want to do this, everything has to have a coefficient of 1. So the problem here is having this 4 in front. And so what we can do with this 4 is turn that into an exponent on the x. So this is going to turn into log base 5 of x to the 4th. And that's it. That's all we had to do, and we're all done. All right, and so we can kind of do the same thing here. This -3 is going to turn into an exponent on that x. So this is going to turn into log base 6 of x to the -3. Now, anytime you have a negative exponent, it's not happy. So you know you have to go ahead and make that a positive exponent. And so we could say, well, our next step then is to rewrite this as log base 6 of 1 over x cubed. Right? And so by taking that x to the -3rd and putting that in the denominator, we can make that exponent positive, and then everything's all good. And that's our answer, and we're all done. Okay, so this next one has a bit more going on to it, but that's okay. The first thing that's good for us is that our arguments are both 6. Our arguments are the same, so then that means that we can combine things. And the first thing I'm going to do is I'm going to take these coefficients in the front. Let's see, I've got these coefficients of 3 and then of 4. I'm going to take those and I'm going to turn them into my exponents on the arguments. So my first step will be to rewrite this as log base 6 of x cubed minus log base 6 of y to the 4th. And now I have subtraction between the two, so then that means I can combine these using division. So then I'll rewrite this as log base 6 of x cubed over y to the 4th, right? And so that's my answer, and I'm all done. Now, this next one is a bit more complicated because we have more going on. We have 3 different logs. So we've got some mixes of division and multiplication going on. And so how we're going to deal with this is anything that is positive, that's going to go in the top of the fraction. Anything that is negative will go in the bottom of the fraction. Right? So another way to think about this is anything that's positive turns into a numerator, and anything that's negative turns into a denominator. Okay, and so the first thing that I want to do here is take all these coefficients that are in the front, and they're going to become the exponents on the arguments. So if I do just that step, I'm going to have, let's see, log base 3 of x cubed minus log base 3 of y squared plus log base 3 of z cubed. And so now I can go ahead and combine things. So I get only just one log. So remember, we said everything that's positive turns into our numerator and everything that's negative goes into the denominator. So this is going to give me log base 3, and I'll have an x cubed up top Actually, I'm going to do this on the next line just so I get more space. Yeah, so I'll do this down here. I'll have log base 3. I'll have x cubed up top. Okay, this negative log base 3y squared, that's going to put my y squared in the denominator because that log is negative. And then this plus log base 3z cubed, that z cubed will go up top. So we'll put that up top. That's our answer. And we're all done, right? So the key there is knowing that any of the logarithms that are positive, their argument goes in the numerator, and any of the logarithms that are negative, their argument goes in the denominator, and you can combine everything in one step. All right, now this next example looks kind of confusing because we've got parentheses and a 1/3, okay? But it's not so bad. So first thing I'll do is I'll distribute the 1/3 across. Well, actually, there are a bunch of ways we could do this. I think the best way to do this is probably to leave the 1/3 for later. I think the fastest way to do this is leave the 1/3 for the end and work with what we have inside the parentheses first. Yeah. Okay, so if we work with what we have inside the parentheses first, we've got subtraction between them, so that's going to turn into division. So what we'll have for our first step is we'll have 1/3, and then we'll have a log base 6 x over z. So all I did was combine the logs inside the parentheses. And I guess if you wanted to throw the parentheses around, you could, but it's not really going to matter because then you end up still just having, that's just the same thing as having 1/3 multiplied by that whole logarithm. So now you know that when we have these coefficients out in front, they turn into the exponent on our argument. So you could think about this as log base 6 of x over z, and the whole thing is raised to an exponent of 1/3. And you could leave that 1/3 there, but really, when we have fractional exponents, we like to rewrite that as radicals. And so having an exponent of 1/3, remember, is the same thing as having a cube root, right? That was the whole thing about chapter 7. So then this is going to turn into log base 6 of the cube root of x over z. And so that's your answer there. Alrighty, so now we can take care of this next example in the same way. We can deal with our parentheses first before we deal with what's outside of them. So let's see, if I have 5 log base 3 of x minus 3, right? And then I can combine my logs on the inside. Well, I've got subtraction between them, so that's going to turn into division. So then this will be log base 3 of y over z. Okay, so the tricky thing here, trying to figure this one out. Okay, I think for this example, it's because we have a negative in front, I think it's actually better to distribute the negative first. I think if we don't do that, then we're going to run into problems. So, okay, so let's talk about the differences between this example right here with the 1/3 in front and then this one right here. So the reason why it was okay for us to deal with what was inside the parentheses first was because what we had outside of the parentheses was positive. So that wasn't going to change anything inside. But if we look at this example down here, we've got a negative. And so you know from all of your experience in algebra, when you distribute a negative, that's going to flip your sign. So we really should deal with that first. Okay? So, sorry for the confusion. Let's go ahead and distribute that negative first. So if I distribute that negative, that'll flip that one to positive. So I'm going to have 5 log base 3x minus 3 log base 3y plus log base 3z. Okay, so now I've got, oops, and you know what? Geez, that's a negative 3, so I should have a 3 in front right here. So this should be plus 3 log base 3z, right? Because I distributed the whole negative 3. And I have a negative 3 in front of the middle one. That one was easy to handle. Okay, so now I've got all these coefficients. So all of these coefficients that are in front of my logs can turn into the exponents on the arguments. And so if we take care of that step, we'll get log base 3 of x to the 5th minus log base 3 of y cubed plus log base 3 of z cubed. Okay, and then now what we can do is now we've got our situation where we can combine things into one logarithm, and from what we talked about earlier, anything that's positive goes in the numerator and anything that's negative goes in the denominator. Okay, so we'll have log base 3 x to the 5th in the numerator, and so this next one, this negative log base 3y cubed, because that's negative, that'll throw the y cubed in the denominator, and then plus log base 3z cubed, that'll throw the z cubed up top, right? And so there is our answer there, and that's it for that example. Now, for this next one, this is like the one that we had earlier, where what we have out in front is positive. So we can get away with not distributing that first and going ahead and simplifying what's inside of our radicals first. Okay, so if I do that, I'll hold on to my 1/2 on the outside, and I'll start off by taking these coefficients in front, right, and changing them to exponents on my arguments. So that'll give me log base 5 x to the 5th minus log base 5 y cubed plus log base 5 of z. Okay, and so now I can combine those into one logarithm. So I'll still have the 1/2 on the outside, and it'll be log base 5. So I'll have x to the 5th up top. I'll have a y cubed down below, and then I'll have a z up top because that one is positive. So now, and we can put all this in parentheses. So I've got this 1/2, and this 1/2 can turn into an exponent out here. And so if I do that step, I'm going to get log base 5 of x to the 5th z over y cubed, and this whole thing is raised to the power of 1/2. And you know, if you have anything raised to the power of 1/2, that's the same thing as having a square root, right? 1/2 is the same thing. An exponent of 1/2 is the same thing as a square root. So we can say this is log base 5 of x to the 5th z over y cubed, and we're taking the square root of all of that. And actually, if you're taking the square root of all of that, you can probably get away with not having those parentheses there. That'll be okay. It won't make a difference, but so then there's your answer there. All right, now example 3, this is different. So what we're doing in example 3 is the reverse of what we did in example 2, and we're writing everything in expanded form, and we can say without a coefficient of 1. So without a coefficient of 1. So this first example, log base 2 of x cubed, that exponent of 3, that will come in front, and your answer will actually be 3 log base 2 of x. And so that's all you have to do for that example, is just take your exponent and kick that on the outside. Okay, now this next one, we've got division, and so remember we said anything that is in the numerator becomes positive and anything in the denominator becomes negative. So this is going to turn into log base 6 of u to the 4th, that's the positive piece, minus log base 6 of v to the 5th. And then the next step is to take these coefficients and throw them in front, or take these exponents and throw them in front as coefficients. So if we do that, we'll have 4 log base 6 of u minus 5 log base 6 of v, right? And so that's our answer there, and we're all done. And so all of these rules that we've learned today for logs also apply to natural logs, okay? So this next piece here, we can do all the same rules that we've just talked about, even though it's a natural log. So all of this is multiplication, so I'll start off by splitting it all up with addition. So this will become natural log of x plus the natural log of y cubed plus the natural log of z squared. And then remember, these exponents will go to the front as coefficients. So then this will turn into the natural log of x plus 3 natural log of y plus 2 natural log of z, right? And that's our answer there, and we're all done. Okay, so this next one, well, we've got a cube root here. So the first thing I'm going to do is rewrite this as log base 6, and instead of having a cube root, I'm going to rewrite it all as being raised to the power of 1/3. Okay? And then what I'm going to do is, I'm going to take this 1/3 and I'm going to distribute that to the exponents on the inside. So I'm going to give every single piece its separate exponent. So then this is going to turn into log base 6 of r to the 2/3, right? Because it's 2 times 1/3, and then w to the 1/3 because that's 1 times 1/3. Okay, so now every piece of the argument has their own exponent. So now what I'm going to do is go ahead and, well, they're being multiplied, so I'll separate these using addition. So then this is going to turn into log base 6 of r to the 2/3 plus log base 6 of w to the 1/3, okay? So I've separated those with addition, so now I can take those coefficients, or those exponents, and turn them into coefficients, and so those will go in front of each log. And so if I do that, I'm going to have 2/3 log base 6 of r plus 1/3 log base 6 of w. And so here's my answer there, and I'm all done. For this next example, we have, let's see, log base 5 of x squared over y, and that's the square root of that. So the first thing I'll do is I'll rewrite this as log base 5 of x squared to the y, and I'll put this all in parentheses, and I'll say that's raised to the power of 1/2, okay? So then what I can do is I can take this exponent of 1/2 and distribute it to the pieces inside the parentheses. And so I can rewrite every piece of that fraction with a separate exponent. And so if I do that, I'll get log base 5 of x to the 1, because, let's see, if you think about that, if you go off to the side and think about that, 2 times 1/2, well, that's just 2 over 2, which is just 1. So that's x to the 1. You don't have to write your exponent if it's 1. And then we'll have y to the 1/2. Okay? And then now I can separate those pieces of the fraction using subtraction. So then this turns into log base 5 of x minus log base 5 of y to the 1/2. And then the last step, this exponent of 1/2, that can go in front of your logarithm here as a coefficient. So then this turns into log base 5 of x minus 1/2 log base 5 of y. And that's it, and you're all done. So another rule that we have to talk about is the logarithmic property of 1. And so for any positive real number b, and b not being equal to 1, if you have log base b of any number at all of 1, it equals 0. So for example 4, these are really easy. Log base 2 of 1, well, it doesn't matter what this 2 is, but as long as this is a 1, then that's just 0. And the same thing down here, log base 6 of 1. Well, as long as that's 1, then your whole thing is just 0, okay? So the inverse property of logarithms, so what this says here, for any positive real numbers b and b not being equal to 1, so that's kind of the same condition that we've been talking about all class. If you have log base b of x, then the whole thing is just x. So what that means is if your base and your argument are the same, the whole thing equals your exponent on your argument. So I'll give you a quick example. If you have log base 4 of 4 to the third, it just equals 3. Or if you have log base 7 of 7 to the 2.1, your answer is just 2.1. Okay? So when your base and your argument are exactly the same, your answer is the exponent on your argument. And then the one-to-one property says that if your bases are the same and you have one log on either side of the equal sign set equal to each other, then your arguments also have to be equal. And so then we can come up with this relationship where you can drop your logs and set your arguments equal to each other. And so then you can just say x equals y. And so we can use that to roll into example 5 where we solve some of these equations. So in example 5, we have to solve for x. We have log base 2 of x equals log base 2 of 64. Well, if you notice, they both have a base of 2, so then we can drop the bases and drop the logs, and we can say that x equals 64, and just like that, we've solved for x, and we're all done. So the next problem, log base 6 of x, right? So same bases, equals log base 6 of 12. So we drop our logs, we drop our bases, and we can say that x equals 12. And again, we're all done. So this next rule is called the change of base formula, and this is what allows you to find the logs and the natural logs in your calculator. And so what this says here is that if you have the log of some base a, let's say log base a of n, you can split it up and you can use any base at all in your logarithm. And so you can take your argument, this n, and you can throw it in as the argument in your numerator, and then you can take your base of a and you can throw that in as your argument in the log in the denominator. And so then if you use a base of 10 for a common log, or if you use a base of e for a natural log, then you can plug that into your calculator and you can evaluate any log at all. So for example, in example 6, we have this log base 5 of 8. We can split this up and we can rewrite this. This is the same thing as log 8 divided by log 5, right? And so you notice I don't have any base written, so I can assume my base is 10, and I can punch this into my calculator. So I'll just do log of 8, hit enter, right? And then I do divided by log of 5, hit enter, and I should get 1.292. And that's my answer there, okay? And then you can also do this with natural logs. So I could do the natural log of 8. Let's see, I'm running out of room here. I could do the natural log of 8 divided by the natural log of 5, and I would get the same answer. So if I use my natural log key, natural log of 8, hit enter, divided by the natural log of 5, hit enter, and I get the same thing, okay? 1.292. When you're doing this, be careful with your parentheses. Be careful where you put in your parentheses and where you put in your division sign when you're plugging these into your calculator. If you get an error, chances are it's because you've made a mistake with your parentheses in your calculator. So for this next one, log base 4 of 12, we can rewrite this with our change of base formula as log 12 over log 4. And how we would punch this into our calculator is you would push your log button, right? and then you would type in 12, and then you could you would close the parentheses, right? So that means closing the parentheses, and then you would do your division sign, and then you would do another log, and you would do 4, and then you would close the parentheses again, and then you would do enter. Okay, so be careful with those parentheses. And then the answer that you should get would be 1.79248. So we'll round that to 1.79. Yeah, we'll leave that at 1.792. That's good enough. All right, so log base 6 of 30. We can rewrite this as log 30 divided by log 6. Okay, so in my calculator, do log 30, close the parentheses, divided by log 6. Close the parentheses, hit enter, and if I round it, I'll get 1.898. So this one, log base 9 of 5, that'll turn into log 5 divided by log 9. So punching this in, I've got log 5, close the parentheses, divided by log 9, close the parentheses, hit enter, and you're going to get 0.732. All right, so now we have this, so log base 3 of 2.9, this is going to turn into log 2.9 divided by log 3, right? So log 2.9, close the parentheses, divided by log 3, close the parentheses, and we're going to get, let's see, if we round this, we'll get 0.969. All right, so I think this is the last example. Let's see. Yes, this is the last example. So we've got log base 7 of 1.2. This will turn into log of 1.2 over log 7. And so if we punch this into our calculator, we're going to have log 1.2, close the parentheses, divided by log 7. Close the parentheses, and if we round that, we will get 0.094 as our answer. So that's it. Those are all the examples, and that's everything we're going to cover today. I hope that helps, and you can try the homework on your own.